at the University of Bradford. He is presently professor there of chemical engineering and leads the Advanced Materials Engineering Research and Knowledge Transfer Group of the Interdisciplinary Research Center in Polymer Science and Technology. This is one of the world leading centers on this matter, so he's in a very interesting place to work. His research focuses on developing new processes to manufacture materials with advanced properties, like composites and other structural materials. And as a consequence of his interest in these materials, he is engaged in fundamental research in applied rheology, in polymer processing operations, and coating flows related to the production of these materials. I would like to mention that Professor Benkreira has worked on projects related to sustainability. For example, he has contributed to the Hosanna. He's a member of the founding member of the European Coating Society, has more than 100 papers related on his subjects of interest, and he's a member of the editorial board of Coatings and the Journal of Coating Technology. So he has a vast experience on this subject, and I'm sure his talk will be of interest for many of us. The subject of his talk is the advances on dynamic wetting in coating flows. And I leave you to make your presentation. Thank you for participating in our conference.
Okay, thank you very much for your kind invitation, and thank you very much for the introduction. My talk, as the title says, I will be talking about advances in dynamic wetting in coating flow. And rather than presenting you a review of other people's work, I will concentrate mainly on our contributions. And at the outset, I would like to tell you that this work is in my group, and I've had over the years many students and collaborators. So this is not just my work, it's the work of my research group. Okay. Now, when you think about coating flows, the first thing that you have to realize is that there are hundreds of coating operations possible. And I show you on the left-hand side, for example, deep coating, where you have a web going into a trough and then coming back and withdrawing a liquid. Next to it, as you see, we have a slot where you could have 1 or 2 or 3 layers. And then on the third one, you are looking at curtain coating, where the like elevate, so that there is curtaining on the substrate. And on the far right-hand side, you have roll coating. And this is just 4 examples. But in all cases, as you see by the star indicated, the web is going to meet the liquid and then form a film at the very end. So the thing which is of interest in here is this region, which we call the dynamic wetting line. This region in here, this region in here, this region in here, and this region in here. And what you see when you look at all coating flow, you can really simulate them in this very simple way. You have a moving web, as you see in here, and the web will have a certain topology. It can be rough, it can be hydrophilic, or it can be hydrophobic. And then you have a film that is coming, a liquid that is coming, and as the substrate is moving, as the web is moving, you form a film, and this is the final film that you make on your substrate. For example, it's here, in this situation it is here, and in this situation it is here. So you can immediately realize that if you're going to go at high speed, eventually the dynamic wetting line is not going to be sustained and it's going to fail. It's going to break. And this is what we talk about, dynamic wetting failure. And at that situation, above a certain speed, then what you're going to have, the air or the gas, which is in here, will be entrained into the film. And as a result, you will have a film which is full of air. And naturally, this is a limit to the production rate, because ideally, you would like to go at as high a speed as possible. Okay? So really the problem from the very basic definition, we deduce that dynamic wetting failure occurs in all coating flows. And gas, air, or any other gas can be entrained, and we will have the corresponding gas entrainment wet speed. Naturally, it will depend, of course, it will depend on the ambient gas in here. It will depend on the property of the web. It will depend on the property of the fluid. And of course, when we say the property of the fluid, we include in that also the hydrodynamic of the fluid. Because when you look in this situation, for example, in deep coating, you are withdrawing a liquid from a trough where there is no movement. Whereas if you look at the situation in here in the curtain coating, you have a flow of liquid which is impinging on the dynamic wetting line. So you have a different hydrodynamic situation in here, in here, in here, and in here. So the dynamic wetting line region will be affected by the coating fluid, the property of the gas, the moving web surface, and the incoming fluid hydrodynamic. So what will I present in this talk? What I'll present in this talk is our contribution to the understanding of the nature of dynamic wetting and to the role of each of these four effects on dynamic wetting failure. That is, the effect of the coating fluid property, the effect of the ambient gas, the effect of the moving web surface, and the effect on the incoming fluid hydrodynamic. Right, so let's try first of all to try to understand the nature of dynamic wetting. And if you look, and the best way to study the nature of dynamic wetting is to use a deep coater, where you see in here you have a substrate, and the substrate is plunging into a bath of liquid. And then if you observe what is happening at the interface in here, you will be able to look at how air is entrained. And the way air is entrained, what happened is when you go above the line is normally straight, turns into a V shape. So you'll have almost like a sawtooth. And at the tip of the saw teeth, you will have air entrainment. So imagine normally, I can't play this movie unfortunately, imagine the dynamic wetting line is straight, but then above the air entrainment speed, you will have a series of V's, and then at the end, you will have air being taken at the tip of these V's. So the situation is that you have, as you see in here, the wetting line is trying to advance normal to itself. So, and when you look at this, you will have the maximum speed of wetting in here, which I'm calling U star. And this is what two researchers, very famous researcher in dynamic wetting, Blake and Rorschach, in 1979, postulated. They postulated that there is a maximum speed of wetting. And the implication, when we looked at the research, the implication was that if instead of going straight in this way, if you slant your substrate in this way, then you should be able to increase the speed of wetting. And this was the first set of experiment that we have done. And I'm going to describe them in here. So imagine in here, instead of going in this way, you entering the bath at an angle. So what will happen? The V's will be inclined now, as you see in this figure. And then if you resolve the velocities, you will see that effectively the speed of air entrainment will be increased by 1 over cos beta. So simply by slanting the web, you are going to increase the air entrainment speed. And this is a corollary of the concept of the maximum speed of wetting. And we went ahead and did the experiment. Here, as you see, this is the coating rig where we have the deep coater, and we simply tilt it. We simply tilt it at an angle and then drive the substrate in this way so that the substrates enter at an angle. And then when we measured the air entrainment speed, what we observed that the air entrainment speed increased as you increase the angle, so much so that it actually doubled at 60 degrees, which correspond to 1 over cos alpha. 1 over cos 60 is equal to 2. So effectively, we could already double the production rate simply by changing the angle of entry into the wetting line. And you can think, of course, possibly when you think of this operation, you may think that it is not feasible, but you can see that if you look, for example, at curtain coating, or you look at slot coating, all it means is by turning your slot coater at a certain angle, by increasing the angle slightly, you can increase the production rate. Of course, you do not have to increase it by a large angle, so you might increase it, you might want to increase it, say, by 10% or 20%, so you'll have to tilt it only very slightly. Okay, so that is finding number 1, which is very important. And we tested this concept using various fluids with viscosity in the range from 60 to 200 millipascal. And also we changed the surface tension and the density. And throughout, as you see, when we non-dimensionalize the air entrainment speed by the cos of beta, the cos of the inclination, then we find that everything returned to 1. So that is finding number 1. And throughout my talk, you will see how I put the corresponding reference in here, which is Chem & Science in 1998 for that particular work. Okay, so that's one thing about the nature of dynamic wetting failure. Now let's look at the physics. How do the physical property of the coating fluid affect dynamic wetting? Now, there have been a lot of work before us, of course, in 1976 and in 1982. In 1976, Burley and Kennedy looked at the effect of viscosity, density, surface tension, and Guthoff and Kendrick in 1982 look at the effect of viscosity. And the net result, when you look at all the data, is that the viscosity is the important parameter. And you will understand later on why the viscosity is very important. And you see in here, in the range of viscosity, say between 50 to 250, you can almost quadruple the air entrainment speed. So at about 250 millipascal, the air entrainment speed would be just slightly more above, about 0.2 meter per second. But then if you decrease your viscosity to about 10 millipascal second, then you will be able to coat in excess of 1 meter per second. So this very simple correlation is very useful to actually try to predict what kind of viscosity do you need in order to be able to coat at a certain speed. And remember that this figure in this equation in here, the viscosity is given in millipascal. So be very careful when you use this equation. And the other important thing when you try to look at other parameters, the only other parameter that affects the air entrainment speed is surface tension. Surface tension decrease the air entrainment speed substantially, particularly at the lowest viscosity. But grossly speaking, it is not really very important. The important variable is viscosity. And the reason is because you cannot change surface tension by much. The majority of the fluid will have a surface tension near, say, 60, and then you'll have to go, and even if you go low, you will never go lower than about 20 or 25. So the changes in surface tension is not as important as viscosity, and that is the reason why the controlling effect is in fact the viscosity. Now, now you ask yourself, why is viscosity is important? Of course, viscosity is important because what is wetting? Wetting is effectively displacing the air, and air is a fluid also. So what you are doing, you're displacing air against a viscosity of a liquid. So really, the effect of the liquid viscosity is to retard wetting. But when you think about viscosity immediately, because we're talking about displacement of air absorbed on the substrate, so we must be thinking about the viscosity very, very near the surface of the substrate, not the bulk viscosity. And that is our first observation that we did. And we thought, okay, if this is the case, then if we are going to do air entrainment measurement with non-Newtonian fluid, we should be surprised to look that the bulk viscosity of a non-Newtonian fluid does not really affect the air entrainment speed, but it is the viscosity of the solvent fluid that is going to affect the air entrainment. And I will explain this very clearly. So if you take, for example, and we did some experiment, glycerin in water, and then we added some PAA or some CMC in order to change the rheology of the fluid. As you see in here, let's say, of course, these, if you take CMC and PAA, they will be shear thinning. As you see in here, the viscosity for the PAA into glycerin in water is going down. As you increase the concentration of the PAA is going to 59, 51, 85, 96, and this is at 400 reciprocal second. But of course, the glycerin in it, the glycerin solution, it's only 51. It's about 50 to, it doesn't change much. So as you see, the solvent viscosity has not changed, even though the viscosity of the whole fluid has changed. And it's the same when you're looking at CMC. If you increase it to 100 ppm, 250, 500, 1,000, you can have viscosities, apparent viscosity of 62, 84, 100, 132, but the solvent viscosity still stays the same. It's still glycerin and water. So, etc. for all the other fluid that we are showing in here. So when we looked at the air entrainment velocity, we saw no difference. We saw really what matters was the base fluid that was controlling the air entrainment velocity. And if you see in here, these are all the data put all together, and in here also all the data put together. So we see that the small addition of polymer affect the rheology of the solution significantly, but the critical velocity for dynamic weighting failure is very little affected. And the work, as you see in here, is the IAC Journal 1998. So what we are saying, that what is important is the rheology at the microscopic scale. So that is lesson number 2 in relation to the fluid properties. And that is very interesting, because if you are doing practical design of a coating line, you should be using only this equation as far as predicting the air entrainment speed. Even if you are using a non-Newtonian fluid, which is made of a solution mixed with other component, you look at the base solution, and it is the base solution, which of course is going to be Newtonian, which is the one that is going to dictate the air entrainment speed. And that took us then to the next important property, which is what is the effect of the gas fluid properties. And the reason why we should put them into consideration is we have to go back to the definition of what is coating. As you see in here, most of the experiments of coating, people have done them with air. And so when we talk about air entrainment, the reason why we say air entrainment is that in practice, coating is always carried out under an atmosphere of air. But then you say to yourself, what happened if instead of using air, I use another gas? And what happened even further? What happened if I could control the viscosity of the gas? So as you see, if I could control the viscosity of the gas, if the gas had a really very low viscosity compared to the viscosity of air, then of course it will not be entrained as easily. And that is the hypothesis that we made when we propose to do those experiments that I'm going to talk about next. So what we did, we took our coater, as you see, and we encased it in a gas chamber. And in this gas chamber, we could change the atmosphere. We could put air, we could put CO2, we could put helium. And furthermore, we also decreased the pressure. And we decreased the pressure to such an extent that we could affect the viscosity of the gas. So we went as low as 10 millibar. But we not only used the deep coater, as you see in here, but also we inserted a slot coater, a slot die overall, like you see in here. This is the slot, and this is the roller. Or we also inserted the slot die over tension web, which is essentially the same slot die, but instead of driving the substrate around the roller, we drove the substrate between two rollers, so we have it tensed around the slot. So this is why it is called slot die over tension web. And then our proposition was, what are we going to observe? Are we going to decrease or increase the velocity of air entrainment? As we propose, we say this is what should happen. So let's see at the data. The first thing then, before we look at the data, at the time, before we did our experiment, there were two theories for air entrainment. There was one which is attributed to Scriven and his student Miyamoto. And the idea, according to Scriven, was that air is always entrained. It's just that we do not see it. it is absorbed, it is dissolved. It's only when it can no longer be dissolved that you have air entrainment. And this is the hypothesis of Scriven. The other hypothesis, which is more, which is on looking at grossly when you look at the V lines, is that air is suddenly entrained. It's only when you go above a certain velocity, you will have the situation that I have described earlier, which is this one. You will turn from a straight line into a line which is made of V's, and at the apex of the V's, the air entrained. So it has nothing to do with dissolution of the air into the liquid. So the first thing that we wanted to do is to say which of these two theories really holds. And prior to our experiment, there has been no experiment to really check this hypothesis number one. So what we did, the first experiment, we looked in this situation, rather than we looked at the air bubble that were being entrapped into the liquid as you decrease the pressure. And as you see in here, we did experiment at atmospheric pressure, and then we reduce it 500 millibar, 300 millibar, 150 millibar, 75 millibar, and this is using silicone and in air. So as you see in here, when you are doing it at atmospheric pressure, after about less than 10 seconds, the bubble all collapse and they're all dissolving. When you do it at 500 millibar, it takes more. It takes about a minute before the air is dissolved completely. Now, when you go at 300 millibar, the air is not dissolving into the liquid. And when you go to 150 millibar and 75 millibar, the bubble, instead of dissolving, they were growing. So a corollary to this argument is thus that air entrainment at lower pressure should occur at lower speed than atmospheric pressure because it's not dissolving. Okay, let's see if that is true. Then we did exactly the same experiment with CO2 and with helium, and again we saw exactly the same thing. With CO2, atmospheric pressure, boom, collapse. 500, it'll take longer. 300, it stopped collapsing. 150, instead of collapsing, they grow. 75, they grow. And observe the rate of growth and the rate of collapse for air and CO2 is pretty similar. However, for helium, it's very different. It takes much, much longer. So helium, the helium rate of collapse and growth are significantly lower. So again, according to argument one, helium should entrain air at or gas. Helium should be entrained at much lower pressure than air and CO2. So we went and then observed the air entrainment speed or the gas entrainment speed. With air, it will be air entrainment speed. With CO2, it will be CO2 entrainment speed. And with helium, it will be helium entrainment speed, naturally. And there we have it. Quite the opposite. In fact, when we reduced the pressure, the gas entrainment speed increased. Look at for helium, it's much higher. For air and CO2, it's pretty much the same, but it's still increasing. So immediately, argument number one does not hold. The extent of dissolution has no bearing on the gas entrainment velocity. it is the gas entrainment is a sudden catastrophic event that happened. It has nothing to do with the dissolution of the gas into the fluid. And then you ask yourself, why is it that helium, compared to CO2 and compared to air, display much higher dynamic, gas entrainment velocities? Why is this? And that was our next set of experiment that we did and theory that we developed. What we observed is when we plotted the viscosity of these three gases against pressure, we see that the viscosity of the air and the viscosity of CO2 are pretty much the same, but the viscosity of helium is quite different, much, much lower, particularly at very low pressures. And once we correlated the entrainment speed versus gas viscosity, we could bring all the curve all together into a single line as gas entrainment speed versus viscosity. But then, which viscosity are we talking about? We are not talking about the bulk viscosity of the gas. Again, we are talking about the thin film viscosity of the gas. And I go back again to the definition of that I started with at the very beginning. What matters is the viscosity of the gas very, very near the very near the surface, not the viscosity of the gas in here. And how are you going to measure that viscosity? That's the next thing. Luckily, we did not have to do that because some other researchers, Andrew and Harris, and many others, if you look in the literature, when you look at micromechanical pressure sensors, where you have plates which are vibrating and they are only like 2 micron apart, then you can measure the resistance. Effectively, you are measuring a thin film gas viscosity. And in that situation, you can correlate that particular viscosity with pressure, and also you can correlate it with the mean free path. So you have a direct correlation between mean free path, pressure, and viscosity. And this is why we were able to produce this graph in here of these viscosities of CO2, of air, and of helium, and how all the data for the three gases that we use collapse into a master curve. So we proved that really what is important again is the thin film viscosity. In the same ways that we proved with non-Newtonian fluid, what matters is the viscosity of the fluid, the liquid, the coating liquid, very near the surface. So everything makes sense in the sense that when you are looking at air entrainment or gas entrainment, you should be looking at the property of the gas near the web, the property of the liquid near the web, and therefore, by implication, you should also be looking at the property of the web itself on the surface of the web. And that was the next set of experiment that we were proposing to do. But before I get to that, we checked our finding by doing the experiment on gas entrainment using slot coating, slot overall, and there is the result. At atmosphere and at atmospheric pressure, there is the minimum film thickness that we could have. That is the maximum speed that we could reach. And when we use helium, at 25 millibar, we were able to coat at much thinner. That is, we were able to go at much higher speed. But of course, in this situation, we could not go at very, very high speed. Typically we obtain a 70% reduction. The reason being that in our very crude chamber that we use, we could not go below 15-20 millibar. So if we could do experiment at much lower pressures than 25 millibar, we would go even lower. And when we look again at slot over tension web coating, we had more success, in the sense that at 25 millibar, for the particular geometry of web tension coating, we could actually obtain a 25% reduction in the minimum achievable web thickness, or effectively we could double the speed of the operation. So the proof is irrefutable that by controlling the atmosphere of the gas, you can control the gas entrainment speed. And what we propose, the control parameter in here, is the thin film viscosity of the gas. So as I said, the next thing, therefore, was to look at the property of the substrate itself, very close on the surface. And then when you look at the property of the surface, what we did, we used our deep coater and we plunged a substrate that had a smooth side and a rough side into a pool of liquid. And you see here is the substrate plunging. It has on this side it's smooth, and on this side is rough. And then observe that at 40 millipascal, the rough side entrain air much sooner than the smooth side. So at 40 millipascal, the smooth side performs better. Now, then we increased the viscosity. We went 60, 70, 80, 90, 140. At 140 millipascal and above, 100, 200, 250, we observe the opposite. Now, as you see, the rough side, the smooth side has entrained air at much lower viscosity, at much lower speed than the rough side. So in here at high viscosity, the rough side is performing better. And we found in between this range of viscosity, one viscosity and one viscosity alone, where there is a switch, where both sides entrain air at the same speed. So effectively, here is the result of the data. This is the air entrainment for the smooth side, and this is the air entrainment for the rough side. On above 84 millipascal, the rough side is performing better, and below 84 millipascal, the smooth side is performing better. So as you see, the roughness has a very complicated and non-linear type of effect. And before we did this experiment, the idea was if you use a rough substrate, you will always coat faster, which is not true. You will only coat faster with a rough substrate above a certain viscosity. So we say to ourselves, we say to ourselves, let's try these with other substrate. And let's combine these effect of roughness and combine the effect of vacuum, that is changing the viscosity, and see whether we can even have more gain. And the gain is really very, very significant. So when you combine the reduction of viscosity of the gas with a rough substrate, then you really have a very good performance. And look at how in here the air entrainment has shot up from about 0.18 to 0.70. So the combination of low gas viscosity and roughness causes the air entrainment to increase significantly. And we did a lot of other experiments with paper, the same thing in here, as you see, to show the point that really there is a critical viscosity. It doesn't always hold. It has to be above a certain viscosity. It has to be, in these cases with paper, because they have a particular roughness, we find that the switch was about 120. So as you see, at 145, the high viscosity, at high viscosity, the rough is always much better. So we say to ourselves, can we underpin this with some theoretical concept? How am I doing with time, please? Hello?
You have 2 minutes, but you can extend a bit if you want.
Okay. Now, when we look at the theoretically, we can see that the film that can be entrained as a function, an air film that can be entrained, is the same. You know, it's proportional to the power 2/3 with the capillary number, whether you have a gas or whether you have a liquid. And when you combine these with the roughness, and if we assume that the film, the air film is going to be housed into the roughness, then you can have a direct correlation between the air entrainment velocity and the roughness. And also you will see the nonlinearity of the viscosity of the liquid. And that explains why we need, there is a change, there is a critical value of the viscosity before the roughness become effective. And actually we observe the same thing in curtain coating. And these are, if you look at the work of Clark later on, he also observed that with curtain coating there is a switch where these phenomena happen. And of course in curtain coating the gain is much higher because you have hydrodynamic assistance. Now let's look at the hydrodynamic effect. Now, even with the normal coating situation, and this is some recent work that we've just published, where we looked at the situation where you have a web which is wrapped around the roller, and you're bringing a film, and in here you're looking at the air entrainment in that situation. And even in that situation, we observe that by playing with the hydrodynamic in here, simply by changing the wrap angle, you can affect the air entrainment velocity significantly as against, for example, deep coating. And this is the line for the situation if you try to predict it using no hydrodynamic assistance, which is like in a deep coater. And this is the situation in here with playing with the angle, with the small wrap angle. And you see we are talking about in here a wrap angle of only a few degrees. And the same thing here you see the wrap angle going from about 1 to about 5 degrees, and it causes the dynamic wetting line to move in here, and it causes the bead to be much stable. So the hydrodynamic around the dynamic wetting line is very important in the assistance of wetting. And we prove that also even in a normal roll coater, if you control the feed film, normally when you have a roll coating situation, the film that come in here is flooded. The nip is flooded. But if you control the thickness of your film coming in to make it very thin, then you can coat at much higher speed than you would coat when it is flooded. All right, so it's a good time because my conclusion, I've reached the end of my talk, and I think I have given you enough experimental evidence to show you that the effect on dynamic wetting of the property of the coating fluid, the property of the surrounding gas, the property of the moving web surface, and the property of the incoming fluid hydrodynamic. And the key lesson to really understand is the property must be the one which are very, very near the surface. But surprisingly, we still have not developed a full theory on dynamic wetting. And I hope some of the audience, some of the researchers sitting in here, some young students will be able to take this work that I have described and as an experimental evidence to develop a new theory for dynamic wetting. And I thank you for your attention, and I acknowledge, of course, all my research co-workers. Thank you.
Thank you, Professor Benkreira. I suppose there are many questions because this subject has many implications and applications. So we are open to any question that can have the audience.
Yeah, can you read me the question so I can answer them?
Yes. I do have some questions, in fact.
Yes.
There is a limit. If you decrease too much the pressure of the surrounding gas, you're in fact somehow changing the viscosity, because there is, for very rarefied gases, you have a relation between viscosity and pressure. Have you tried this? Because you are saying it's better to reduce the pressure, but there is a limit for that?
Yes. Yeah, you know, strictly speaking, if you go to zero pressure, you'll have no gas. So yes, the air entrainment speed would be infinity, or the gas entrainment speed would be infinity.
Yeah. So this analysis is restricted to a particular regime, I say.
Yes, it is. In our case, of course, we could not go, because of our experimental difficulties, we did not go below 10, 15, 25 millibar. All right. Okay. But even in that situation, the thin film viscosity is changing. And the way you measure the thin film viscosity, you have to use, because viscosity does not mean anything if you do not look at at what you mean by it. And in our experiment, we're talking about viscosity in a gap which is very, very small.
The other point is you're using somehow, you're emphasizing the importance of microscopic details of the flow very, very near to the contact line. And you're using Blake approximation. But you're also saying that the incoming fluid hydrodynamics could play a role in this entrainment. So have you tried some matching between the incoming fluid hydrodynamics and the microscopic approach used by Blake for example, using models like those developed by Petrov, which combines Cox-Voinov with Blake's study of the contact line?
Yes, this is what we are doing currently. Yes, this is why I presented the data, but our next work that we are going to publish is to try to link the two together. You're correct.
We have a question from Diego Campana. He asks you, have you conducted any experiments to check if the molecular polymer size, for example, influence the air entrainment?
Yes, that by implication, by using these CMCs and PAA, the molecular size is very large. And so therefore, it would not be effective near the interface. And this is why I refer to the solvent viscosity. So if you have a solution of a liquid with a polymer of high molecular weight, you should be able to find exactly the same behavior as we describe in here. So I don't think there have been a lot of work that followed the work that we have done, but the person who has asked, it's a very good question. It will be good to repeat this experiment using a solvent and changing the molecular weight of the polymer. That would be a very good research program to really underpin what we have presented in this paper, which I describe in here.
You are now unmuted.
1998.
Thanks you for your answer. Gaston Nino has a question.
No, it isn't. Not at infinite rate of deformation. The only reason we put in here the viscosity at high shear rate, because we were trying to find out which viscosity is important. And we realized it didn't matter, because the viscosity at high shear rate was the lowest viscosity that could be attained. But that lowest viscosity was still not as near as the viscosity of the solvent. But good question again, because strictly speaking, it isn't the low shear or the mu infinity of a shear thinning fluid. It is the solvent viscosity.
Okay. There's Herman Grace is writing questions. Just wait a minute. Perhaps you want to speak, Herman? I could unblock you.
Okay. Thank you. So thank you for your talk. So I was a little bit confused about the bubble experiment you showed growing and shrinking. And I was wondering, is the liquid in equilibrium with the gas at the pressure inside the chamber?
What do you mean? I'm not clear what you mean.
Well, I'm not sure you're injecting the liquid from inside the chamber, but does it have time to equilibrate with the gas for any absorption?
No, we don't inject any liquid. the liquid is in the bath in here in the trough, and we simply change the pressure.
¿Sí? Hola. 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 Sí. Pero para, mi señora no está, así que no, sí, pero mi señora no está, que la que lo pongo, así que no te puedo decir nada.
Sorry, I can't hear somebody else talking.
Okay, so what I was trying to ask is because you showed some examples in which the bubbles will grow or decrease,
Yes,
right?
Yeah.
So is that when the liquid is already saturated with the gas or not?
Yes.
At the same pressure as you inject the gas, the bubble.
Yes.
And so they grow because they are recruiting gas from the liquid?
Yes, that's correct. Yes.
Okay.
And for further, have I given the reference? I think the reference, the reference is Benkreira and Aikin. So you can, and if you're not very clear, please email me and I'll send you the paper describing exactly the what we've done, all the procedure.
Sure. And then let me ask you another question. So when you talk about the viscosity of the gas in a thin film, so what are you referring to, a particular scale, or how do you, when you said you took it from the literature, but is this for some length scale in particular, or is valid for what kind of confinement?
No, we only took the experimental data from Andrew and Harris, where he did the 2 micrometer separation, and he used several gases. I can't remember exactly, but there was a correlation between the mean free path and the pressure, and because we knew the property of the air and the carbon and the helium, we could close the circle and find this correlation in here for the effective viscosity. We did not measure them.
If it is different from, as you mentioned, it's different from bulk, so wouldn't it depend on that 2 microns? If it is 1 micron or 10 microns, or
possibly, yes, certainly, yes. Yeah, it has to be. And this is the assumption. Ideally, as lower separation as possible, but you can imagine 1995 damping sensors, already at that 2 micron apart, that was pretty small for us. But of course, if it is going to be like a millimeter, it won't be good enough. It will be.
Thank you.
In that situation, it will be bulk viscosities.
Well,
which will not change very much.
Well, we thank you, all the participants, and especially to Professor Benkreira for his talk. We should finish the question time now, but if anybody has any questions, I'm sure Professor Benkreira will receive them by mail gladly, I suppose.
I will be very, very happy. Yes, just email me and I will reply to you for sure.
Thank you very much to everybody, and especially to Professor Benkreira. And we will resume our meetings after lunch. Thank you very much to everybody, and we declare finished this session.
Thank you, Alejandro. Thank you.
Not at all.
Okay.
Thank you to you.
Bye-bye.